Yeah, so much so for simple random sampling, covering some aspects of width replacement with special emphasis to the estimates based on sample with distinct units. That was something new for you, I believe. Our next topic is stratified random sampling. I am sure you are all familiar with the basics, namely formation of strata, why are the strata formed, what is the advantage, and then stratified random sampling, what it means, how do we come up with an estimate of the population mean, population total, and expression for the variance of the estimate written as V suffix strat, and then the allocation problem, proportional allocation, Neyman's optimal allocation, and the formulae, and then the resulting expressions for the variance, and the basic inequalities involving V ran, V prop, V opt. All these things have been taught, and these things are covered in theoretical classes as well as with practical assignments. What is so far not known is implementation of the allocation design, allocation plan with particular reference to the Neyman's optimal allocation plan, what are the practical difficulties, and there is an exciting, very exciting novel technique that has come up only recently, and I will emphasize on that. So, with that background, let us get into the topic of stratified random sampling. So, as I said, let us start with stratified random sampling. I am sure, as I said, you know all the basic results, including allocation problem and allocation formulae, particularly Neyman's optimal allocation. As you know, that reads like NH opt equal to N NHSH over summation NHSH. That can also be expressed as N WHSH over summation WHSH, which we write as N PH over summation PH, PH being equal to WHSH. So, what is the basic idea? Capital N is the total sample size of the finite population under question. Typically, we write capital L for the number of strata, and for the hth stratum, the stratum size is capital NH, the stratum variance is SH square, and the stratum weight is WH, which is NH over capital N. And the Neyman's optimal allocation formula reads like, for a total sample size small n, the sample size, the optimal allocation of n into the hth stratum is given by the formula NH opt equal to small n pH over summation pH. So, recently I got to know about a highly interesting and revealing algorithm for implementation of Neyman's allocation results. That is what I wanted to discuss. So, let me describe through a small example. All the notations are standard, you got it in Cochrane's book, for example. So, we start with 7 strata with a total of 30 sample size, and the overall sample size 30, and let me show straight away the pH values, because these are the things that are ultimately involved into the expression for NH opt. So, pH values I show them in descending order with some permutation of the stratum levels. So, the pH values in descending order are 37.341, 25.768, etc. So, it is 37, 25, 19, 18, 12, 11, 12, 11, etc. And the total is this. Neyman's optimal allocation, if I apply the formula, that yields 8.11, 5.60, etc., and that gives a total of 30. However, I have to do integer approximation. So, let us see what we are up to. 8.11 we write as 8, 5.60 we write as 6, 4.22 we write as 4, etc. We are just making decimal approximation, integer approximation to these numbers, giving a total of 8, 6, 4, 4, 3, 3, 3, just by doing numerical approximation. That gives a total of 31, but our total is 30, so we need to cut down one of them, and I wrote there are 4 options to cut down by 1, and we can think of 5.60. Instead of rounding it to 6, we can round it up to 5. Or for example 2.70, it was rounded to 3, maybe we can round it to 2, etc., etc. There are 4 possibilities of doing it. However, the optimal solution needs exact computation. So what is normally done is you look at all the 4 options depending on which one you are approximating and in how, giving a total of 30, you write down the actual expression for the V strat under each of these options, and then you compute the minimum variance, and thereby you come up with the result. So optimal solution needs exact computation, and it turns out to be 8544333. Out of the 4, you compare the variance expressions and you find that this is the optimal allocation. So usual approach suggests NH opt values to be ascertained from the pool of possible options. That is the usual approach. In this example, we had 4 options. We work out V stat under all the options, and then we try to find out the allocation which gives the minimum. So that is what we do. But if there are a large number of strata, then of course this approach is not very easy to take up. In principle, you know what is happening, but it's kind of difficult, time consuming. So we need to take all possibilities subject to the total of 30 units and decide on the best allocation result. This is the general approach that we know. As against the above algorithm, the following computational algorithm is worth noting. This is prompted by a recent article by Dr. Tommy Wright of the US Bureau of Census. It is published in a very popular journal, The American Statistician, only very recently in 2012. So let us look back at the expression for V of Y versus STRT strat, V strat, as is known. In usual notations, this is the expression for V strat for the estimate of the population mean using stratified sampling and the allocation numbers NH. So it is a very straightforward expression, summation WH square SH square 1 over little NH minus 1 over capital NH. You can split into 2 parts. The first part depends on the sample size NH, and the second part is of course a constant for our purpose. So for minimizing the variance, for ascertaining optimal allocation, it is enough to look only to the first part. Now we may rewrite the first term as it is summation WH square SH square over NH. That 1 over NH we can write as 1 minus 1 over NH. That's fine. So the first part now becomes summation WH square and minus summation the same thing times 1 minus 1 over NH. And because we want to minimize this expression, it is as good as maximizing the second part with a negative sign, namely maximizing what we call T1 star, summation WH square SH square into 1 minus 1 over NH, subject to a fixed total summation NH equal to n. And this is how the thinking process goes, that 1 minus 1 over NH you can write as 1 minus 1 half, plus 1 half minus 1 third, plus 1 third minus 1 fourth, and so on. And that simplifies to 1 over 1 into 2, plus 1 over 2 into 3, plus 1 over 3 into 4, and so on. So that tells you that you should possibly start with a two-way table of K versus pH square times 1 over K into K plus 1 for K equal to 1, 2, 3, etc. for each of the stratum where pH is nothing but WH, SH. So you know the WH and SH values, you compute pH square, and that you divide by K into K plus 1, and let K be the running index 1, 2, 3, etc. For doing this computation, we may arrange the strata in descending order of the pH values. That is what we did. I said without any loss, let the pH values, let the strata be so labeled that the pH values are in descending order. That is what we are doing, and we are preparing this table, and once the table is prepared, we simply make top selection from all over the table and keep a count of small n selections when we stop. Because the idea is we want to maximize summation WH square, summation PH square multiplied by this 1 minus 1 over NH is factored into different components. So the general term is 1 over k into k plus 1. So we just write a two-way table and we start making the top selection from all over the table, keeping a count of small n selections when we stop. This yields Nevin's optimal allocation results. It is easy to implement and it naturally stops without any integer approximation problem as encountered before. We are aware that we need at least 2 observations from each datum. That being so, we may as well start by selecting outright the first column k equal to 2 in the above table and then go for the top selection from the rest. At times, unconstrained selection may ensure this as well. Let's take up a small example. For the above data, that numerical values that we have shown before, indicating the values of pH, we have this two-way table like this. So what is the first row represent? First row picks up the highest value of p square, which is given in the beginning, and that multiplied by 1 over 2 into 3, next one 1 over 3 into 4, next one 1 over 4 into 5, and so on. So this 26.40, 15.24, 10.78, etc., they are all arising out of the products pH square divided by k into k plus 1, k ranging from 2 onwards. So you can see the whole table, the first row corresponding to the first value of pH, the max, the next one corresponds to the next value of pH, and so on. These are the 7 rows, and for every row we have the expansion pH square divided by k into k plus 1. We need a sample of 30. From this, because we have to maximize this expression, we start making top selection. So 26.40 is the absolute max. Next one is 18.22. Next one is 13.73. Next one is 15.24. Next 13.73. Next 13.36. Next 10.78. So as you can see, it is going all over. It is rushing among all the 7 strata and always picking up the highest numbers. Then it comes to 8.81, 8.72, then it goes to 8.39, then it goes to 8.35, and so on. You just go on making a note of the hand-picked top numbers, top selection, and you go on making a count of 30. The moment you got 30, you stop. So this is what has been done. All the numbers shown in italics are picked up, and then at the end you stop with a total of 30. You remember k equal to 2 means there are 3 observations, k equal to 3 means there are 4 observations, and so on. So at the end, an unconstrained sample of size 30 is exhibited above by italicizing the top 30 members, and realized sample sizes are 8544333 with a total of 30 as indicated above by the traditional approach. So the traditional approach gave me 8544333. By using this technique, we come up with 8544333 instantly by referring to the values of the top selection according to this method. So this method it depends on the fact that you can rewrite the expression for the variance, the general term, you can rewrite in the form of this pH square multiplied by the expression that we have, you can put in the form of a two-way table of values, and that is the basic idea. Not only that, there is something more fascinating to the above table. Suppose from practical considerations, we stipulate minimum sample sizes across different strata. The first stratum I have to have 3, next one I have to have 3, and so on. These are the minimum sample sizes in different strata. That gives a total of 21. So that in effect, we only need additional 9 units to be selected. If this is the constraint given to us, we straight away make these advanced selections in the table and then go for top selection from the leftover for variance computation. So for example, 3332244, those are the things mentioned here, 3332244. All the figures marked in bold, they refer to the selection subject to the constraint of having 3 from the first stratum, again 3 from the second stratum, and so on. And after that, once all these 21 have been picked up, then the remaining 9 are picked up again by referring to the remaining part of the table and making top selection. That gives you 10.70, 7.72, 7.8.35, 7.29, etc. Note that there is no reason why the leftover numbers should exceed the numbers that have been picked up. Whenever we picked up the numbers according to the constraint, for the last stratum, the numbers came down to 3.34. It does not matter whether this number is more or less than the rest. Definitely it is much less than the leftover numbers, but it was a physical constraint, so it had to be taken up. So whatever be your constraint, you take care of those numbers in the beginning and then go for selection of the top selection from the remaining numbers. This is an added advantage of this implementation, and we will have some questions and queries to answer to have a better understanding about this method. This time we started our discussion on stratified random sampling, a topic reasonably taken up in undergraduate studies. You all have first-hand idea about the basics in stratified random sampling. I particularly stressed on implementation of the formula for Neumann's optimal allocation, which is called NH-opt, and we know the formula. We know how to use it traditionally. We do the computations using this formula for NH-opt, which is NWHSH over summation WHSH. I wrote PH for WH times SH. Formula is pretty simple. As we apply, we get numbers with decimals. We have to make an approximation to match with the number little n. While doing the approximation, there are several possibilities. We write down all the options, and under every option we work out V strat, we compare them, and we come up with the optimal allocation. This is what is usually done. Here I talked about a paper recently brought out in the American Statistician by Dr. Tommy Wright, head of the Statistics Division of US Bureau of Census, and he suggested that we can work out this optimal allocation by referring to a two-way table, by going for maximization of certain objective function, and by making top selection from this two-way table, going all over all the row. Every row represents the stratum contribution, and across different rows we have the components, and it is a matter of handpicking the maximum numbers right from the beginning. Even if there are constraints, practical constraints, like the minimum number to be sampled from each stratum that is laid down beforehand, we can use that beforehand. We can take all these numbers, and then from the leftover two-way table we can make a top selection. So the method seems to be very handy. We will take up some numerical examples to see, and some questions to see the relevance of this technique. Yeah, I propose to take up 4 theoretical questions, and for all the questions we need some data set, and for all the questions the following data set is available. We have 7 strata. We have the stratum sizes like 12, 14, 14, etc. We have the stratum standard deviations 2.5, 3.2, etc. So this is the basic data table that is given to us, and based on these figures we have to sort out certain theoretical problems. Okay, I invite you to read one by one.
Question 1. For stratified random sampling using Neumann's optimal allocation, illustrate Tommy Wright's computational algorithm for a population of capital N equals 120 units distributed in L equals 7 strata, and for a total sample size of N equals 50.
Okay, so this is a straightforward problem. Once we have understood what is going on, we write down, we prepare that two-way table, and this time we have to pick up a sample of size n equal to 50. So we make top selection there are 7 strata, a lot of things going on, and we have to start counting the top numbers across all the rows till we hit a total of 50. Okay, the only point that has not been mentioned here, if by chance there are 2 numbers which are equal, by chance 2 numbers which are equal, then if that is in the beginning, we select both of them. But if that happens at the end, suppose the 50th pickup and the 50th pickup, whatever we pick up, and that is the same as the 51st pickup, then we can take any of these 2 without any problem. So that is the only point that I thought I should make. Let's read the next question.
Question 2. Do the same when there is a need for minimum allocation sizes to be 2, 3, 3, 2, 2, 3, 4 respectively.
So as I said, if there is any constraint, then we first put that constraint. So in the 2A table, we make a deliberate selection of the units such that all these numbers are represented. So we have 2 from the first one, 3 from the second one, and so on. And after that, these are made bold as in the text. And after that, we go for making selection out of for the remaining. This total is 2 plus 3 plus 3, 8 plus 2, 10, plus 4 plus 3 plus 2. The total is 19. So 19 are taken. Still we have to go for additional 31. After having selected these things, marked in bold, then we go for making selection of 31 top numbers from the 2A table. That's the whole idea here. What is the next question?
Question 3. Do the same when the minimum allocation size needed is 3 for each stratum.
Okay, so this time it says 3 for each stratum, 3 times 7, 21 gone, remaining 29 we have to figure out by making the top selection from the table. But every time we go all over, once these numbers have been fixed, then we have to go all over for the selection of the remaining items. When we select 3 for each stratum, we don't care about the numbers, whether they are big or small. Anyway, they have to be included. Okay, what is the next one?
Question 4. Do the same when the first 2 strata, the minimum allocation sizes are stipulated to be 3 and 5 respectively.
Very good. So earlier in question number 2 and question number 3, it stipulated the minimum allocation size for every stratum. This one says, imagine only in the first stratum, the stipulated sample size is 3, and in the second stratum, the stipulated sample size is 5. So this is the minimum. So the minimum allocation sizes are 3 and 5. How do you go about it? So all you do, in the first one you put 3, and in the second one you put 5, and then you make it open. So that minimum restriction is over, is imposed already. Now you make it open and start selecting from everywhere. That is the idea of this question. Let us see what are the MCQs.
Question 1.
Yeah.
Tommy Wright's algorithm leads to proportional allocation when n is more than twice L. Is it always true? May be true. True if n is more than 4 times L, and none of the above.
Okay. I did not tell about proportional allocation as such, but you must be knowing proportional allocation in the context of stratified sampling. When small nh is proportional to capital NH, we call it a proportional allocation. So there the formula is small nh equal to small n times WH, WH being the relative weight of the hth stratum. So that is the background that you have, small nh equal to 2 a small n times WH. So given that understanding about proportional allocation, is it that the Tommy Wright's algorithm that we have seen by preparing the 2A table and picking the top numbers, it leads to proportional allocation? Is it that the Tommy Wright's algorithm, it leads to proportional allocation when n greater than 2L? That is the question. Whether it is always true, maybe true, etc. Now you can think about this problem. What is the next one?
Tommy Wright's algorithm may not lead to a valid allocation in case n is not more than thrice L. Is it always true? May be true. True if n more than 4 times small n, or none of the above.
Very good. So we know what Tommy Wright's algorithm is talking about. It is based on a preparation of the 2A table and then going for it. Now when we say valid allocation, the only validity that we talk or care about is that at least 2 observations should be taken from every stratum. So if small n is more than 2l, that's good enough for us to be able to insert as an imposition 2 from every statum. That takes care of 2l, and the excess number n minus 2l that we can use Tommy's algorithm to get it. Therefore, it is true that we don't need n greater than 3l, n greater than 2l is good enough for you to come up with a valid allocation. If valid allocation means that you should have at least 2 observations per statum. What is the next one?
Tommy Wright's algorithm leads to optimal allocation with each ni more than 3, when n is more than thrice l. Is it always true? Maybe true. True if capital N is more than 6l, and none of the above.
There are all kinds of weird questions and weird options given here. Let's see again. Every small ni greater than 3, if small n is greater than 3l, then of course small ni greater than 3 implies n has to be greater than 3l. There is no question about it. So maybe the spirit of this allocation, the problem is this algorithm leads to optimal allocation with each ni greater than 3 when n greater than 3l, but not necessarily, as you know. Even if n is greater than 3l, when handpicking the numbers, we don't necessarily follow small ni greater than 3, that restriction. It could at best be small ni strictly greater than or equal to 2. So unless this is an imposition on the allocation numbers, there is no reason why ni should be greater than 3, even though n is greater than 3l.
Tommy Wright's algorithm fails to work if capital N is not divisible by capital L. Is that always true?
There are some options given, but at least in the example that we saw, we didn't even care about whether capital N is divisible by capital N or not. All we really need to know is capital N is at least 2 times capital L, and we can impose the condition that every statum has to have 2 observations. Otherwise, variance estimation from within the statum becomes impossible. That's the only restriction that we can have. So there is no reason why capital N should be divisible by L. There is no stipulation like that in the whole algorithm.